Okay, so let's talk about post tension and the reinforcement zones, what they typically look like. VSL is the company that was working on FIU bridge collapse when it collapsed. So even though they have a great technical manual here, they obviously did not. They consider themselves an expert on repair and things like that. They're responsible for the death of their own worker and for citizens below. So, through triangulation, just because somebody wears the halo hat and they look good, it does not mean they're good, right? They went after the money. I don't know. I think it was only 45 grand extra, something thereabouts, to do that repost tensioning of the structure. That ordered by Denny Pate and allowed by FDOT and everybody, all the other engineers there. I want to talk to you about the reinforcement zones now. This is a typical image, or a image rather. Oh, this one looks pretty good. So, interesting enough, reinforced, and let's just think about this for a second, because I can use this even though this says force, right? And this says reinforcement. Well, forget all this. It's kind of complicated to drive yourself crazy. Let me get you the basics of what you really want to just consider. And then I'm going to show you something, a video on it. So I'm doing this live as I do with you guys, so I don't have these images programmed. So we'll just use it for narrative reasons. Let's call this our dead end. The end the cable is in, and then you use something to clamp it. And now on the other end, you pull tension on this cable with a tooling device. I showed you that tooling device that I have, and it puts tension in this cable. The issues are that the dead end, and also the live end can happen also, but the dead end, I'm going to show you a video on, it's going to fail. I want you to look at this, and this is just a wedge in the opening in the concrete to be able to put grout back in, let's say. Here's another version of it. I want you to think about this. This dead end is just a bolt back there, a big giant nut. All right, so it's big giant me back there, nut job, crazy guy, right? All right, so let's go like this. Yeah, I can make fun of myself. I don't have that issue. They also use a twisted wire wire cable technique that I really like that one myself. It seems like it might distribute a lot less. Now I want to think of this as zones. Here we are. I like this one at the top. Yeah, I like this one a lot at the top. You'll see it looking like it looks like a spring. Look, it looks like a spring. See the spring action going on? But I want you to think of this spring now, and I want you now to look at a column going in the ground, and I want you to think of that tree again. Remember the tree, the stirrup design that I showed you guys about how trees are nature's natural stirrups? They have growth rings, you guys call them, and reality is the nature's natural stirrups that allow the tree. We're looking at a cutaway of this tree now, the growth rings you guys would call them, right? But they're stirrups. And as a tree sways, this way and that way, these stirrups, some go in compression, some go in tension, and across here too, both all around, they all participate in keeping the tree stable. If you see concrete going into the ground and you see the spirals, these long tubes going to the ground, looks like that, and then you'll see rebar like that, these cages, but they're round. And you'll see them. Well, imagine that here that cage is now turned on its side, and this is what you're looking like. And the spiral is just a fancy cage that's laid down real simple. That's all it is. And the spiral is the nature's. It's trying to duplicate nature's. If you think about it my way, it's nature's stirrups. So here's a round one. Here's this bolt, right? This connection. And it's in the middle here. As the pressure is in the concrete, so here's the bolt, the nut. Yeah, it's just start. Well, might as well go for it. Look, so there's the nut. Anyway, so the tension is created in this cable here. is anchored by that bolt. The pressure is created in a zone down here around the concrete. Imagine it was just no concrete. It was sand, if you will. You know, it can't hold it. So now it's start increasing it. Now make it a stiffer sand and then a more stiffer sand. It still can't hold much, can it? You can still pull it through with your hand. Now use a very weak cement. Oh my gosh, you can still push through it. Still push through it. So now what happens is the same thing with sand, but now I tell you to put your anchor back 100 foot deep in the sand and now try to pull it through. You're like, oh, that's different. I can't do that. Not only and pretend like it was in a pipe all the way up to there, because you'll have to displace all that sand in front of it. And I say put it in a pipe because I want you to have the ability I don't want you to think of surface tension of the cable. It's just laying there. It's dead weight cable on the pipe, if you will. And you'll be able to pull it, but the anchor's back here in the sand. It's a lot of sand you got to displace, right? But you can imagine that the sand helps with that force, all that concrete now. And now a weaker concrete's not as good as a real more strong concrete. And then what's even stronger, it makes it even stronger, is to do the stirrup system. Confine the forces that want to come out of this bolt as we look at it from the top view. Confine it with stirrups, the steel. Well, confine it in concrete, but don't allow the concrete to burst away by putting stirrups around it. Nature stirrups would be the steel. So you're just looking at 2 layers of nature stirrups here. A tighter zone, this zigzaggy thing, and then a larger zone. So you're basically looking at a tree with just, so here's the bolt, and then there's one set of stirrups, and there's your second set. So here's your primary of trying to keep these forces from going out, and then your secondary out here to keep them to confine it again. So you can imagine it would be even better to have multiple stirrups around there, but it more cost prohibitive now. It gets a little crazy for you, right, for people. And so it doesn't work as much. It's not used as much. It's not used at all. They just use pretty much 2 rings like that. And as you can see, this ring configuration has got a very odd duct with it, right? Imagine it's trying to force down. So this would put translate, or this would try to act as 1 because of all the reinforcement. So this block of concrete would then start pushing on this block of concrete, which pushes on all the way down to this concrete below it here, and then here are stirrups trying to keep this from blowing out. See the stirrups? I'm data stacking this for you. I have somewhere I want to go. I want to talk to you guys about cantilevers and also spans. Then I'll cut to the chase a bit for engineers out there that might be impatient. I think cantilevers and decks, just not based on 9 inches, should have a top layer, upper layer, and have configurations similar to this. I was trying to see how I could duplicate it, improve my point, because I've had this quite a few videos loaded up and they're sitting there waiting to go. And I'm like, you know what? I think I can do better as I wait day after day and few weeks go by. And I'm like, you know what? I think I can get this across a little more better because I wanted to get across to engineers. Invert this darn thing here. Invert it and turn it into a cantilever. This. And now, well, I'm going to back to the bracket thing. I'm going to show you what happens if we put hook stirrups here on the steel only. I want the steel to be so strong in its linkage that if you had this welded, you'd now be able to start loading it without the concrete. So it becomes redundant is what I'm trying to drive at. I want the steel to be redundant to the concrete. Also being that factor, remember concrete, that as far as I know, I'm the only one that talks about the steel needing to be in compression back here to keep this cantilever from rotation. Because if I cut this away, this corner away, it will rotate. So this is proving that the bottom steel is even needed. Bottom steel is even needed for redundancy. I'm going to add more to that as we go, but I want to show you that. Now I'm going to show you this to help you understand it a little better. There's a video that it took me forever to find a video. So we're going to watch right about here, the contractor knows this is going to fail because he states that there goes number 3, meaning or implying, I believe, that he's up to number 3 of bursting, and so it's now predictable that the dead end, because this is not the end that they're adding the tension on. Well, it's all the way through, but this is failing. Now, this is the concrete pad. I know it's bad lighting, but we take what we can. He's probably protecting his face. I'll put it on his camera too. This is the concrete, and there's the pad here, right? There you see the pad in the background, and this is like a shadow up at the right of his finger, probably right here, blocking the view. I'll get this cleaned up for you in a second. So now I want you to think about, I guess I'll clean that up now. I want you to think about the concrete. There it is again, right? And these are the rebars sticking out. I mean the cable sticking out. I want you to think about the forces I just mentioned, how they're trapped in a stirrup. Well, in this case, we have the earth trapping it. It's concrete there already. So the bursting effect, the earth is going to trap it down here along with the concrete that's connected to the earth. And let's just use a circle, that recycle thing as my refresh as where the rebar is, where the anchor is, or below it in the concrete. And the cable goes down that length, let's just state, and have it sticking out a bit. It wouldn't be sticking out that much, but they're going to add another, I don't know why they're doing it that way, they are. So then it was ease of length, wasting cable. But anyway, so let's go. So the anchor is here, this is your anchor. The cable is here. The anchor is the one I just told you about, the forces. And remember, so around it will be stirrups, right? And then the concrete matters. But now let's go ahead and get rid of those stirrups. That puts the force. I'm not saying this pad doesn't have stirrups. I mean the stirrups. It probably does not. I've seen a lot of people in these pads not use stirrups and the concrete. So the concrete's probably not mature enough. And so what's going to happen is it's going to fail. But let's look at this. So here's the concrete. I want you to do this. I'm going to give it a little cheat now. And this is earth. That's the earth. So as you load this, you can see the forces go this way. Okay, there's plenty of concrete here. And they go this side too. Plenty of concrete there. And below they got plenty of concrete. So sort of like a Claymore mine, since this is all covered with backed up with a non-moving position, the concrete on this side, concrete on this side, concrete at the bottom, and the earth here, where would the forces burst out from? Where would the most forces be concentrated from? This is on a pad on grade. Well, it has no choice but to go up. It gets no choice but to go up and back. It would be up and back, and the ricochet of it would be, as it hits the forces or in the concrete there, it might come back just a little bit, but mostly up is where it's going to get its released. Now let's watch the video. Oh, okay, right about yay. Here we go.
Line back.
You saw that? Let's do it again. It's going to burst into the air. Into the air.
Line back.
So that's my best way to show you that the forces are there, whether you like to believe it or not. When you think about concrete, post-tensioning, all, they're there. The forces are internal. It's holding on. It's kinetic. You can say it's not kinetic if you want, and say potential. I really don't care. It's kind of semantics with me with potential and kinetic. They're both energy. So, I don't, a potential energy of a gun that's uncocked and laying there and not ready to fire is nothing. It's not going to do anything. You got to do something. Got to do something kinetic to make it happen, right? So, I don't care which one you choose on that. I'm trolling you a bit too, but don't bite on it if you don't want to. There we go. Bells.
Line back.
Okay, so I was able to pause it. And you see there's a little bit of burst behind the ejection this way, just very small, but most of it was here in the upwards in trajectory. This concrete can find it on here and here. So now I'm helping you predict, as engineers, predict your failure and where it would go. It's the anchored end, it's where it would burst up. It's where it's going to do that. Now, of course, profiles matter. So if that was, why did it burst up? If they had the anchor like this, too aggressive, and then they pulled on it like this, it creates what? Well, that would be a downward force. Okay, so that doesn't make sense because the stresses would be a little turn down right there. Creates, well, it also creates a lot of loss of tension can slacken between this last bit. So that's not very productive. How about this one? That's why you see the slight bit of incline on the tent, on the rod, on the cable. Just a slight bit ramp up. And then let's put a bolt back here. And so now your forces are in there. They come up, they anchor, they ramp up slowly, or you can just go straight if you want. And now going straight, the advantage of that is, say this is your concrete pad, you can see that the forces are going to be equal with the pad. This direction, the forces are going to come down, so the bottom cover really matters. Right, so there's your anchor, and the slope up is the pulling direction is this direction. Whatever direction you go into, that's your direction of forces. So if you don't have enough cover down here, well, they want to put a lot of force downwards and blow out your lower concrete. If you've got this an anchor and going down that way, and then put the cover on it. Whoa. Okay. How do I get that back up? And then put the cover on it. Let's do that again. So this direction, I'm going to go down a slight bit of exaggeration, anchor, concrete. And now the forces applied at that anchor, and this is concrete right here, right? And concrete all over here. We'll want to go this direction. You see how it turned down the cable right there. And it go that direction, all that direction. But in this one, a little bit of cover. Let's say it's about 2 inches of cover up here, along with weak concrete that has matured enough and can relate it to the forces. I'm going to say they didn't tension these these cables, and so it's probably the placement, lack of stirrups, or the not enough concrete above for cover and maturity. End the video, but this would be how I'm just letting you guys, since you're wrong for the failure analysis ride and learning, hopefully this will give you something to think about with post-tensioning, especially you people out west. And there's the chunks of concrete. And that's it. The repair would be another question altogether. After testing the core sample of concrete and checking it, you could repair this. It's not a trash job. Well, you can repair it if it can take the post-tensioning, if the cores come back good enough. All right, end of video. Take care. Hope you enjoy this step. It's got more coming. Bye.